Hey everyone, I'm Major Garret Schmitz. I'm the commander and pilot of the F-16's Viper demonstration team. Thanks for checking out the video, and let's start our walk around of Venom. So probably the first thing that you're going to recognize is it's painted a little differently than every other F-16. So we got the chance about a year ago to come up with our own design. So this is completely team resource, so we came up with the design. We drew all the drawings, all the decals, and then we had it painted at Shaw Air Force Base. So completely internal to Shaw. Something you might want to check out, if you can see on the tail of it, you can see our patch, how it normally has a snake coming out. Well, we extended the snake out, so it's almost like the snake that's on our patch the aircraft is an extension of that snake. So kind of a small detail that a lot of people don't see, but we were pretty happy with it, and the design turned out great. So it's the only one painted like it. So far, I'm the only one who's flown this one, so we'll see if we can keep it that way. But yeah, welcome to Venom, meet the world. We'll start on the left side, and then we'll talk about kind of everything about the Viper as we go. So this is where all the magic happens, obviously the cockpit. Unfortunately, we can't get up there to film it, but this is how we climb in. As a team, we travel with a small collapsible ladder that will fit in a travel pod that we usually put on the middle station here. So it's pretty precarious climbing up. We hook the ladder right there and then climb on up, and then I'm able to control the canopy once I'm inside. In terms of the Viper, so airspeeds that you guys might be curious of. So we have two main airspeeds when we're taking off that we're looking at. That's our rotate speed and our takeoff speed. In a mil power takeoff, our takeoff speed is going to be 10 miles per hour, or 10 knots above our rotate speed, and if we're taking off with full afterburner, it's going to be 15 knots above. And that's all going to be dependent on our configuration. So in a completely clean configuration like this today, on about an 8,000 foot runway, mil power, our rotate speed is going to be about 146 knots with a takeoff speed of about 156 knots, which is a normal takeoff. In the demonstration, when we're flying completely clean, full afterburner takeoff, we do a little more high performance takeoff. So at 100 knots, I'm going to rotate, and my jet's going to lift off at about 120 to 130 knots. And it usually takes about 900 feet, which is an incredibly short distance for an aircraft to be able to take off. So in our normal takeoff configuration in a clean F-16, we weigh about 28,000 pounds, and our engine produces about 30,000 pounds of thrust. So it's an incredibly powerful aircraft for how light it is. So it's a pretty incredible takeoff. It's an exciting takeoff. Definitely forces you back in the seat. Cool. So kind of taking a look at the left side here. So we get into our static probes here. So this is kind of how the Air Force tells, or the aircraft tells, altitude, airspeed is based on the differential between the dynamic pressure, which we get from our pitot tube in the front, and our static pressure, which these are static pressure ports. So we got to make sure those are clear. Those are measuring the ambient static pressure that changes as you climb in altitude or descend in altitude. Kind of moving forward, what we have here is our little AOA probes, or our Aoa Veins. So AOA stands for angle of attack. So this and its corresponding counterpart on the other side, they're going to be affected based on the relative position of our nose compared to the direction we're traveling. So that's what we call angle of attack. So if a good representation of it is if we're traveling this direction but our nose is pointed this direction, then that amount of units, that degree there, will be what our angle of attack is. So the F-16 is limited to 25 degrees of angle of attack. That's computer limited. That's not something I can control. And that's to keep us stable, because this is such a high performing aircraft that it could go beyond that. But once you go beyond 25 units of AOA in this aircraft, it becomes very susceptible to departing. So the engineers built in a Aoa Limiter, which keeps us limited at about 25 degree AOA with our gear up, and then lower AOA once we put our gear down, because we're not as high performance. So these are the probes that measure that. So we've got one on this side and one on the other side. This discolored part, so this is our radar. So this is essentially what I use in the cockpit to cue my air-to-air missiles, to lock up other aircraft, and just to build general SA on what's going on around me. So this is what's called a Mech scan radar, so it's mechanically scanned. So there's actually a plate in there that moves back and forth. mechanically versus some of the newer generation of radars, which are electronically scanned. They're just fixed, and then essentially a computer allows the radar to electronically scan different areas. So they both perform the same job. MechScan is a little older technology, but it's a great radar for the size. When you're talking radar, you're talking about energy produced and absorbed, so size matters in terms of the cross-section of a radar. So the bigger the nose, the more powerful radar you can have. We're a little bit limited because it's a fairly small nose on a Viper, but for this size of a nose for a MechScan radar, it's a really great radar. And it gives you a lot of situational awareness on what's going on. And if you notice the 4 antenna there up above the radar, so that's our AIFF, or that's our IFF interrogator. So IFF stands for Identify Friend Foe. So that gives us the ability to essentially type in a special code and to search for different codes without getting into it too much, into the detail, but it allows us to identify if someone that we locked up or someone who appears on our radar is someone who is a friendly, an unknown, or an adversary. So that gives a lot of capability to the F-16 in terms of a tactical fight. This is our pitot boom. So this is what measures the dynamic pressure of our aircraft. So it'll take, we use the difference between our dynamic and our static pressure. It helps calculate both airspeed and altitude. A lot of people think it's the gun, not the gun. We'll get back to the gun once we get all the way back around. But yeah, so this is our pitot boom. Something I didn't mention, or I kind of touched on a little bit, but different configurations for the F-16. So if you take a look at this F-16 from the front, this is completely clean. This is as clean as you can get an F-16 and still fly it as high performance as we do. So our limits right now are Mach 2.05, which depending on your altitude could be somewhere around 1,500 miles per hour. So it's an incredibly fast aircraft. In this configuration, we can super cruise. So what that means is I can get above the Mach, and without using afterburner, I can still stay above the Mach. So a very sleek layout for the F-16. In terms of max altitude for us in this configuration, easily fly in the 40s with a ceiling of 50,000 feet for the F-16. Looking at the configuration again, so touching on how we're clean. So we can actually load it out with a multiple different variations of configurations. So if we go out in a purely air-to-air sense, what you're gonna see is about, you're gonna have a missile on each wingtip and then 2 more on each wing. So it's a 6x0 or a 5x1 loadout. So what that means is a 6x0 loadout would be a completely AMRAAM loadout. So our AIM 120s, so all IR guided. So, or sorry, not IR guided, so all radar guided. If we do like a 5x1 loadout, that means we're gonna have 5 AMRAAMs and 1 heat-seeking missile. So an AIM-9, either Lima Mike or 9X, and that's gonna be our IR loadout. So that's a pretty common air-to-air configuration. Air-to-ground configuration. So what's unique about Shaw, so if we come back over this direction. So we're one of the only active duty CONUS-based seed unit for F-16s. So what we'll normally have attached to our jet, on kind of our left chin mount here, is our Hts Pod, or it's our Harm Targeting System pod. So what this does is, performing the Wild Weasel mission, we go out, and this pod allows us to know when enemies turn on their radar. It identifies kind of where they're at, and it gives us a location to shoot our HARM to, or our high-speed anti-radiation missile. So that gives us the ability to go out, locate their enemy threat radars, shoot them before they can shoot us, and we're also incredibly maneuverable. It's kind of why the F-16 got the Wild Weasel mission, is because we're able to create miss distance. If we're unable to shoot those enemy SAM systems before they're able to shoot us, we can create miss distance between where that missile is going to explode and where our aircraft is, to hopefully survive it and come out of it alive. So that's kind of a Wild Weasel mission. That's what we normally have, and most Shaw jets are going to have that loaded up. In a seed configuration, we'll go out with probably a 2x or 3x1 scenario for our air-to-air missiles, and we're going to have probably 1 HARM here, so a high-speed anti-radiation missile, or potentially 2 HARMs, one on each side. If we just go out with 1 HARM, we may end up with a couple of 500-pound bombs on the other side, or maybe some 250-pound bombs. Just depends on what the tactical scenario calls for. So that's kind of what our loadout would look like on a normal training day. But this right here, this is the sports version. This is the sports car. We get to go out and essentially show the crowd what the F-16 can do low to the ground at the edge of its envelope. So it's definitely in a pretty awesome configuration right now. All right, so not going to be a whole lot different on this side of the nose. Same kind of stuff that we saw on the other side. Again, for a normal training configuration, for an air-to-ground mission, what we're going to have here. So this would be our targeting pod. So this gives us the ability to essentially both air-to-air and air-to-ground locate things. So we can tie this to our radar. So that if I lock something up with my radar, my targeting pod is looking at it as well. So I can actually take a track and follow an aircraft with my targeting pod once I have them locked up, and break lock with my radar. And so there's no indications to that person that I'm following them. Just my targeting pod will be kind of following them the entire time. So that's a use that we use the targeting pod for an air-to-air mission. It also gives us the ability to identify aircraft at a long range. So if we need to visually identify something, we can see it well beforehand. Well before I'd be able to see it with my eyeballs, we can see it with the targeting pod. So it's a great tool to have to both identify what we're going after and just keep general SA on what's going on out there. In an air-to-ground scenario, this is what we use to locate any type of object or fortification or anything that the ground forces are trying to talk our eyes onto. This pod is very capable. So it's mainly IR, but we can use television as well. But it allows us the ability to find something on the ground, generate coordinates, and then if need be, we can drop a bomb on those coordinates that we generated from our targeting pod. So it gives the F-16 an awesome air-to-ground capability, keeps it definitely very relevant in the air-to-ground game. So if you look right now, a lot of 4th gen is doing the heavy lifting on the majority of our fight that's going on. So Iraq, ISIS, Syria, ISIS to an extent. So this pod and the Hts pod definitely keeps the F-16 and 4th gen in general still in the fight. You see this pin here, so this is what's called that's our EPU pin. So EPU is our emergency power unit. So unlike other aircraft, well, some aircraft have an EPU, some have different systems. What we have is like another little kind of engine here. So if we lose our engine, we only have one, so it's a bad day in general. But right around here, there's what's called our emergency power unit. And this allows us, it provides enough power to our flight control system that we're still able to fly the aircraft. And it's powered by hydrazine, which is a pretty toxic material if it leaks, but very, very rare for it to leak. I've never heard of an EPU leaking hydrazine, but it's a precaution we take, and we test it every day before we go fly. So we have our crew chiefs pull this EPU pin, and then we run up our power, and we ensure that our EPU with a test switch that'll actually turn on if we need it to. So for those that don't know, the F-16 is completely fly-by-wire. So what that means is there's no mechanical connections from our flight controls, like our stick, to our actual flight controls. It's all controlled by the computer, and our stick only moves about that far either direction. So it's purely based on pressure. So the computer senses how much pressure I'm putting on the control stick, and then the computer is telling our flight control surfaces how much to deflect. So if we have they call it the electric jet, it's one of the first completely electric jet. And if we have a complete power failure, you can imagine that'd be very important because we have no mechanical connection. So this EPU is our backup to the multiple redundancies that we have. This is kind of the last resort to make sure that if we need to, we can still control our aircraft. We either get it to a safe place to land or get it into a safe situation that we can safely eject. So a good peace of mind here. Our gear speed in the F-16 is 300 knots. So that's both on takeoff and landing. We're looking for the gear to come up before 300 knots, and then we're not going to low it prior to 300 knots. Other than that, you're not worried too much about gear speed in the F-16. It's all sequenced, so the gear come up first and then our gear doors will close, and then we have light indications in the cockpit for each gear. So left main, right main, and then our nose gear, as well as an indication for the gear doors. We have the ability to emergency extend if our checklist is about that thick, so there's a lot of situations where we would have to emergency extend, but we have the ability to. So if you're looking in our cockpit, our gear handle is going to be right here, then there's going to be a T handle down here that's going to be our emergency extension. So if we need to, we can pull that. We have some pneumatic bottles that will essentially force our gear down. So they're not really gravity fed like some aircraft are, so they're actually forced down by a pressurized system. And then we can use that in event of emergency, but once we use that, that's kind of our last option. So we're not really going to cycle the gear at all once we do that. So if that doesn't work, now we're getting into the conversation of how are we going to land this jet with the configuration that we have. So whether it's a nose gear that didn't come down or a gear that's partially out, we have, again, there's a complete section of our checklist that covers pretty much every eventuality with gear issues. So that's kind of our quick and dirty of our gear system. Taking a look at the rest of this wing here. So we've got our leading edge flaps. So what you'll see kind of during our demo, these are all auto sequence. So we don't have a flap switch in our jet other than a way to go alternate flaps and then to lock our flaps. So if we're having issues with flaps auto sequencing, then we can essentially slow down or speed up to where we want them to be and then lock them. But for the most part, there's no flap switch that I hit when I'm taking off or like raising the gear, lowering the gear, like a lot of aircraft do have. So these are all sequenced by the computer. So the engineers, when they designed the F-16, they made it very easy to fly. So everything in the jet, from the stick placement to the throttle placement, it's very intuitive. It feels like it was built for me. So the engineers did a great job taking feedback from pilots previously and building it to make it as easy as possible to fly. So these are our leading edge flaps, and you can kind of see the trailing edge flaps back there. You can see different hard points here. So when we talk about stations on the F-16, we have 9 stations. So we start from the left and we go to the right. So this is number 9 station, and then we would go 8, 7, 6. We've got 5 kind of on the center line of our aircraft, which is where we usually either have a fuel tank or some type of jamming pod. And then it would just be the same on the other side. All right, so that was essentially the different stations on our wing that we have. Again, we talked about a lot about the air-to-air and air-to-ground loadouts we can have. Usually in an air-to-ground or any like long duration air-to-air, we're gonna have 2 wing tanks instead of putting a centerline tank on. So that gives us the capability to stay airborne without refueling for probably an extra hour to an hour 15 based on what we're doing. And then indefinitely if we're air-to-air refueling, obviously. We talked about the centerline pod or the centerline station. So you can put a multitude of different weapons there or pods. Generally what we're gonna fly with is our electronic countermeasure pod. So what that does is I was talking about the harm targeting system pod and how we use that to locate enemy radar. We use this to jam those radar if they're trying to shoot us. So this pod, I won't get into radar theory about how it works, but essentially it can take in their, essentially the trons that are coming out of enemy radar, manipulate them, send them back out, and either jam an enemy radar or make that enemy radar have difficulties tracking us. So it's a great tool to have. Again, another good peace of mind that you've got a defensive countermeasure, electronic defensive countermeasure, as well as our offensive countermeasures in the harm. There's debate about these. I don't know how much I can talk about these. So right here, so this is called a MERL, is what we call it, or a missile rail. So we fly with these on the aircraft because it gives us the ability to essentially go to the extreme limits of the F-16. So if we were to take these off, we would be airspeed limited and G limited because of what's called wing flutter, which is something they discovered early on with the Viper without any stability out here, is that the wings will resonate and you get a lot of flutter in the wings. So we fly with these, and usually a missile on the rail to give us the capability to go upwards of 9 Gs or above, and into the above the speed of sound range. So normally on a training mission we would have just inert AIM-120s or AIM-9s or other type of pods on the stations 1 and 9, and then it's always incredible to me that we can hang a 500-pound missile on the wing tip and still pull 9 Gs, which turns that 500-pound missile into a 4,500-pound missile, and the wings have no issues with it. So we'll climb up on the wing sometimes, and I was like, oh, I'm not gonna hurt it, but then you think about the 4,500 pounds that this thing's able to withstand under 9 Gs, and it's a hardy machine. So we have the standard complement of lights, so our navigation identification lights. So you can see them on kind of the intake there. We've got our nav lights. Nav lights here, and then we've got our rotating beacon up on the very top of the tail there. We got a whole host of avionics along the spine. So if you just take a look at the kind of the right side view of the whole F-16, so you can take a look at the very front. Obviously the radar that we talked about, the cockpit, and all of our avionics are up there in the cockpit. Other than that, right behind the jet, or right behind the cockpit, there's going to be a fuel, one of our fuel pods. But other than that, this thing is all engine. So you got intake there. Our engine's going to start about right here and go all the way back to the very end. So other than our cockpit, small section of avionics, and a small section for fuel, this aircraft is all jet engine, which is kind of what contributes to the 30,000 pounds of thrust, with us only weighing about 27 to 28,000 pounds. Taking a look along the spine, it's hard to see, but there's a couple of yellow markings right there, and then right behind it is going to be our aerial refueling receptacle. So that's where, when we need to get our jet refueled in the air, we're going to fly it up to behind either the new KC-46, the 135, or the KC-10, and they're going to use their refueling probe to essentially transfer fuel from their aircraft to ours. People always ask if aerial refueling is difficult. Once you get the hang of it, I would say it's not too bad anymore, but it's never incredibly easy. But I think if you deploy once, you're refueling probably 5 or 6 times each mission. So once you do that, you're pretty good for the rest of your career. Kind of continuing back, you can see along the spine some discoloration. So we've got antennas in there, different communication antennas and GPS antennas. So obviously paint is going to interfere with that. So that's kind of why that section is unpainted right there, is we don't want it to interfere with any of our signals coming in or going out. Taking a look at the back, we got kind of our 2 ventral fins right here. So a couple of uses for those. Mainly it protects the tail on landing. So when we land at between 11 and 13 AOA, so that AOA that I was talking about at the front of the jet. We have an indication in our HUD that shows what our angle of attack actually is. So we're shooting to land between 11 and 13 AOA, but if we go 2 degrees more to 15 degrees AOA, that's when we get into the situation where we can strike the tail or the speed brakes, which I'll show you here in a second. So these ventral fins are there to essentially to protect the tail if we have an overshoot of AOA. These things will hit first, and it's a lot cheaper to place something like this, so it's just a panel, versus any of our tail feathers back here, or a scraped speed brake. But it does happen. It's a 2 degree margin that we have, so I don't think I've ever scraped a ventral fin, but it's absolutely something that happens. We'll take a look at our both of our horizontal stabilizers, our vertical stabilizers, and then on our wings as well. We have kind of these static wicks. So this is to dissipate static electricity that builds up on the aircraft to help us avoid getting hit by lightning. Essentially what these are. Taking a look at the back section. So now we're getting into our speed brakes here. So we have a couple different settings for our speed brakes. So we can open them essentially all the way if we need to slow down, or we can, controlled by my left thumb and on my throttle, I can kind of command how far I want the speed brakes to open. And then, so they open incredibly quickly, but then they'll close a lot slower. So if I need to slow down quickly, these things will spread out like this, if I can get, so spread out like that. You can see some water pouring out on both sides, and then they'll close as necessary. So taking a look at our business end of the jet, what you're seeing right in there, so those are our kind of afterburner flame holders. So how an afterburner works, it essentially just dumps fuel into the exhaust of an aircraft, and it's ignited, and then that extra fuel is what gives you your essentially your extra thrust from the afterburner. So that's our afterburner flame holder, our ignition source for the fuel that we dump into our afterburner, and then this whole section is our afterburner. Once it comes out of the afterburner section, it gets into our nozzle section. So again, getting into like gas dynamics or propulsion, the ability for your aircraft to produce a large amount of thrust is largely dependent on the pressure coming out of your aircraft. So if you look at like a MiG-17 that's gonna go fly here today, it has a dirty afterburner, which when I say that, I mean it's just flame coming out. What this does, this nozzle, so as I increase my power, so idle, my nozzle is gonna be open with a low exit pressure. As I increase my my throttle or my power setting up to mil, this nozzle is going to go from fully open to fully closed, and then when I get into afterburner, it's going to slowly open back up. So there's so much pressure coming out of the aircraft. This nozzle is used to equalize that pressure, and that's when this goes a long ways in giving you kind of those shock cones that you see coming out of an afterburner. It's that good, nice tapered cone with individual cones in between it. That's all dependent on our nozzle. So as the pressure increases with our afterburner, this nozzle is going to open up to varying different stages based on what stage our afterburner is at. So if you've ever heard an F-16 coming into land, it's a very loud like whistle, like whoop whoop. So what you're hearing there, that's our nozzle adjusted. So that's our oil system is what we use to adjust the different nozzle positions. So that's kind of our oil pressure activating our nozzle actuators to open and close our nozzle. So if you ever get the chance to kind of be below an F-16 when it's landing, you hear those whoops, that's what that is coming from our aircraft. Not a whole lot different on this side. We'll try to stay over here for the noise wise, but we can talk a little bit more about the F-16. So obviously our configuration is going to determine what our limitations are. So like I said, in this configuration, we have essentially no restrictions. So we're up to 9 Gs. 9.8 per our technical orders is what we can pull in this configuration, but we limit it to 9 Gs just to help reduce the stress on the airframe. You can see aircraft are getting somewhat old. If you look on the back of the aircraft, the first two numbers are the year that it was made. This one was built in 1994. The jet over there was built in 1993.